Hey guys, my name is IBM and I'm taking you through kinematics. Do not forget to subscribe if you want. You can share the videos with your friends. You can leave a comment. I'm always willing to answer your questions and try to rectify. So this is kinematics, and remember we said we have to explore we have to describe motion. We shall talk about uniform accelerated motion, projectile motion. We have already seen speed and velocity. We have talked about acceleration. We have been describing motion in terms of distance and displacement. And we shall see equations of motion later on. Remember, I said kinematics is actually under mechanics. So this is going to be lesson number 2 of kinematics. Lesson 2 of kinematics. So in lesson 1, we basically tried to emphasize that we can describe motion in terms of speed, velocity. We mentioned average speed and average velocity. Um, we mentioned acceleration as the rate of change of velocity. We mentioned distance and displacement. So we can describe motion in terms of those words. So today or in lesson 2, I want us to describe motion using graphs. So lesson 2 will start with describing motion using graphs. So we are going to describe motion using graphs, and we shall start with a position time graph. So this is exactly the same thing you did in GCSE, and it's the same thing I want us to explore at this time. So let's consider the figure drawn here. This is a position time graph, and it is a graph of a body which is moving. Initially, we see the representation is a straight line, and then after some time, we notice that the graph kind of curves, and then after later on we see that it curves downwards. So this is a position time graph. Sometimes someone may want to call it a distance time graph, but for now we shall call it a position time graph. So this figure shows or is a graph of a position x against time t for a particle moving in, say, a straight line. So we are going to describe the motion of this particle by using this graph. What does this graph represent? So we are going to break the motion of this particle into 3 parts. That is O to A, then we can talk about A to B, and maybe B to C. So from O to A, what do we notice? So from O to A, it is a straight line, which is from the origin. And if it is a straight line from the origin, it means in equal time intervals, the particle or the body is covering equal distances. If it is a straight line from O to A, it means that in equal time intervals, the particle is covering equal distances. And whenever the distance is the same, or whenever the distance is constant for a particle, it means that the particle is moving with a uniform or constant speed, or constant velocity for that matter. So that means the average velocity from along O to A would be x1 minus 0 divided by t1 minus 0, and this is going to be a constant value. So from O to A, the average velocity will be x1 minus 0, over t1 minus 0. But because it's a straight line, that is going to give us a constant value. So clearly, this is the gradient of the straight line part of the graph between O and A. So x1, if I'm trying to find average velocity, I just get the final point minus the initial point to find the displacement. Because there has been no change in direction, so it will be x1 minus 0 over t1 minus 0, and that is actually the gradient of that straight line. So because this is the gradient and we see that it is a straight line, then we know that the speed or the velocity or the average velocity along O to A is actually going to be constant. Then let's look at between point A and B. So between A and B, if I wanted to find the average velocity in that case, between A and B, if I wanted to find average velocity in that case, the average velocity there would be x2 minus x1, then divide by, this would be t2 minus t1. That would be the average velocity. However, you notice that between A and B it is not a straight line, which means that even though this is the average velocity, it means the speed is not actually constant. The speed is the average speed or the speed or the instantaneous velocity keeps changing between A and B. And of course, later on we shall understand that actually it is decreasing because the gradient is actually decreasing. So between A and B, the particle is actually slowing down simply because when you look at the graph, it's like it is covering less and less distance as time goes on. So the distances traveled in equal periods of time are getting smaller. For example, when you look at the time at this time here, between this time here and this one here, the change in distance is very small, yet the time interval is relatively big. So the distance traveled in equal periods of time is getting smaller between A and B, so we can say the body is actually slowing down. So precisely, you could simply say that the speed was decreasing, or it was actually decelerating, as we shall see later on when we advance. Okay. So then for a moment, we see that at B, if we look at B, it is almost a horizontal line, which means for a moment, it's like the distance remains constant at B. And if the distance remains constant, it means the object is not moving. So at B, we can say the body is momentarily at rest. And after B, we notice that there is a reversal of direction. If I wanted to find the average velocity from B to C, that would be x3 minus x2 divided by t3 minus t2. But you notice that x2 is bigger than x1, which means that this is going to be a negative value. The average velocity is going to be a negative value. And the negative in this case will also imply that there has been a change or reverse of direction. So it means there has been a change in direction. That's why now the position or the distance is becoming smaller with respect to the origin. There has been a change in direction. That's why we are going to get a negative because x2 is bigger than x3. So when we subtract, we are most likely going to get a negative value. Okay, so at B, we said the particle is momentarily at rest, and after B, it has reversed its direction and is heading back to the origin. It is heading back to where it started from. So it is heading back to the origin. So between B and C, the average velocity is going to be x3 minus x2 divided by t3 minus t2. But because x3 is smaller than x2, we are saying that this value here is going to be a negative. And the negative quantity in this case is going to be reversal or to represent reverse of direction. There has been a change in direction. So whenever there is a change in direction, in other words, whenever we move in the opposite direction to the one we were moving to before, the velocity should be represented with a negative value. So calculating the average velocity of the particle over the relatively longer time intervals, that is T1 from T1 to T2 from T2 to T3, and trying to consider the direction or trying to consider the magnitudes of these values would be enough to tell us that the body was moving in opposite direction after B. In other words, the body was going backwards. So to describe the motion exactly, many times we shall need to know the particle's velocity at every instant in most cases. So that's why I would describe the motion, I would divide this motion into say 3 parts, because I know at between O and A it is a straight line, so it's like the motion can easily be described as uniform velocity or uniform speed. Then between A and B we see that the line is having a decreasing gradient, where we shall later on see that the gradient is actually going to be the velocity. So between A and B, someone would say that, okay, the body is slowing down, so the speed is decreasing because the gradient is decreasing. And between B and C, we notice that one, we shall have a negative gradient. That line has a negative gradient between B and C, which negative gradient means that the velocity is negative, and which negative implies that it is in the opposite directions. But also you notice that this gradient, the gradient of this line between B and C, is increasing. So it is a negative but increasing gradient. So it means the body is moving back but with an increasing velocity or an increasing speed, as we shall understand in more details later on. Okay, so that is a hint, or just to give you a clue about the position time graph. So let's understand the displacement time graph. So there will be little boundaries, there will be almost no boundary between displacement time graph and distance time graph many times, especially for learning purposes. But of course, we know that distance is a vector quantity and yet displacement is a scalar quantity. However, there may not be a very perfect clear boundary between displacement time graphs and velocity time graphs. So let's talk about the displacement time graph. All along we know from GCSE that the gradient of the graph of a displacement time graph is actually equal to the velocity. We know this from GCSE that the gradient of a velocity time graph is equal to the velocity. If I have a displacement time graph, I know that the gradient is actually the velocity. So it means that the steeper the slope, or the greater the gradient, the steeper the gradient, the greater the velocity. So a graph like this one can also tell us if an object is moving forwards or moving backwards. So from a displacement time graph, we can still tell if the object is moving forward or it is moving backwards. Of course, we must ensure that we consider one direction positive and the opposite direction negative. So if the gradient is negative, then the object's velocity is in the negative direction, so it is said to be moving backwards, as we have seen in the previous example. So the gradient of a displacement time graph gives us the velocity, and it means the steeper the gradient or the steeper the slope, the greater the velocity. And I said a graph like this one will tell us whether the object is moving forward or it is moving backwards. And if the gradient is negative, it means the velocity is negative, which means the object is now moving backwards, or it is moving in the opposite direction to which it was moving before. So let's just illustrate these graphs simply. If we have a displacement time graph and the graph is a straight line through the origin, or just a straight line, it may not always be through the origin. So if a graph of displacement against time is a straight line, we say the object is moving with a constant velocity because we have said the gradient is the velocity. The gradient of a straight line is constant. This gradient is not zero. So it is a constant velocity which is not zero, because sometimes the gradient may be constant but zero. So the straight line shows that the object's velocity is constant, because the gradient of a straight line is constant. Other terms we might use could be uniform. We could use the word steady. So when we talk about steady velocity or uniform velocity, it is a straight line, but not zero, moving with a constant velocity. If it is a displacement time graph, it should be a straight line whose gradient is constant but not zero. So that is what we mean by uniform velocity. Gradient is constant and not zero. Because later on when we plot or when we sketch a graph of velocity against time, again we shall see that constant velocity means zero gradient. But this is displacement against time graph. So remember I said if the line is steeper or the gradient is steeper, it means the velocity is higher. And if the line is less steeper, it means the gradient is less steeper, it means the velocity is less steeper. So we can compare two graphs here. So we have two graphs of displacement against time. Compare V with compare the first one with the second one. So a line which is closer to the x-axis is less steeper than a line which is closer to the y-axis. So we can say the second line, the line which is closer to the y-axis is steeper than the line which is closer to the x-axis. Therefore, we can say that the gradient of this line, let me call this one A, is higher than the gradient of B. So which means the velocity of A is higher than the velocity of B because A is steeper than B. And remember, the gradient of the slope is actually the velocity. So the velocity in both cases is constant, but the velocity of line A is higher than that of line B because line A is steeper than line B. So we are saying the gradient of a displacement time graph is the velocity. Okay, let's see what happens if the object is at rest. We are discussing graphs. So for an object at rest, if the object is to be at rest, if you recall the position time graph, we saw that at the tip where the curve was almost horizontal, for position time graph, we said at that moment the body was at rest. So it means if a body is not moving, it means the the displacement should not be changing. The displacement remains constant. So if a displacement time graph gives you a horizontal line, it means the object is at rest. How do we know that the object is at rest? The displacement is not changing. And if I try to find the gradient, remember the gradient of a horizontal line is zero. The gradient of a horizontal line is zero. So the gradient of a horizontal line is zero. And remember the gradient of a displacement time graph is the velocity. So this means the velocity is equal to zero. An object cannot be moving with a zero velocity, not at all. It can move with the zero acceleration, but not with the zero velocity. So this object is at rest if it is a horizontal line. Okay, we can also have a situation where the object moves and then returns, or it goes back to its original, or it moves backwards. In that case, remember we said the gradient should change sign from positive maybe to negative. So let's consider a situation where the object moves backwards. So in the first stage of this motion, this is a displacement time graph. In the first stage of the motion, we have a straight line where the velocity is constant and not zero. And we can say that the first point, the velocity is positive. Then the second stage, the gradient is now negative for this line, which is turning towards the x-axis. So here, the gradient is negative. So if the velocity is positive here and negative here, it means in the second case, the object has changed direction. It is actually moving backwards. Therefore, the object can be said to be on its return journey. So here the object is returning to where it started from. So the slope of this graph suddenly becomes negative. The object is moving back the way it came. So it is moving back to where it came from. Its velocity v is negative after time t. So the first case, the gradient is positive for this line. The second case, the gradient is negative for the other line. So it means a negative gradient is meaning that the velocity is negative, and the minus sign of the velocity shows that the body is moving in the opposite direction to where it came from. It is moving towards where it came from. It is moving towards its starting position. It is moving backwards in the same line, of course. Okay. Let's see a situation where we don't have a straight line. So suppose we don't have a straight line, like this one here, we have a curve. But we notice that this curve is becoming horizontal. And remember, the gradient of a displacement time graph is the velocity. When the curve is becoming horizontal, it means the line is becoming horizontal. And remember, the gradient of a horizontal line is 0. What does that mean? It means that by the time we reached 0, the gradient was decreasing. So if I have a displacement time graph where the curve is becoming horizontal, it means the gradient is decreasing. So here the gradient is decreasing. And at this point here, the gradient equals to 0. So it means the gradient was decreasing to 0. And if the gradient is decreasing to 0, remember the gradient is the velocity. That means the velocity was actually decreasing. And remember, if the velocity of a body is decreasing, it is slowing down, we say the object or the body is decelerating. So the displacement time graph is curved, the slope or gradient is changing. This means the object's velocity is changing. It is not uniform, it is not straight, it is not steady, it is not constant. And I said for this particular motion or for this particular one, the gradient is decreasing. When the line tends to becoming horizontal, the gradient is decreasing. So we say the velocity is decreasing because remember the velocity is the gradient, or the gradient is the velocity. However, notice that the curve I have sketched here is very smooth, which means if I was to find gradients at several equal time intervals, I'll get a uniform decrease in a gradient. And a uniform decrease in a gradient would give a uniform acceleration. So this motion shows decreasing velocity, but because it is a smooth curve, then we would say constant deceleration. If it wasn't constant deceleration, the curve maybe look like this. Not smooth at all, which means at equal time intervals we may not get equal changes in gradient. But because it's a perfectly smooth curve, it means that equal time intervals we are most likely going to get equal change or equal gradients. Or we are going to find equal change in the gradient, which means equal change in the velocity. Therefore, it would be a constant deceleration because remember we said acceleration is change in velocity over time. So if there are equal changes in a velocity between several time intervals until we reach zero gradient, it means that we have constant deceleration because it's going to be a negative since the velocity is decreasing. A lot of us will not be able to see that this is a displacement time graph and the velocity is decreasing because we always associate the word decrease with the graph turning towards the x-axis. But this is a displacement time graph. And we are saying the gradient of a displacement time graph is the velocity. If the gradient is decreasing, then it means the velocity is decreasing. A decrease in velocity is a deceleration, slowing down. But because this is a smooth curve, we can say the velocity is decreasing uniformly. That's why we call it a constant deceleration, a steady deceleration, a uniform deceleration. As an assignment, sketch another graph for which the velocity is increasing. So I'll just sketch this for people who take much time to pick these simple concepts. So if I wanted to demonstrate the fact that the velocity was actually increasing, displacement against time graph for a body of increasing velocity, so I must draw a curve where the gradient is increasing. So I would draw a smooth curve. Okay, so it is just the opposite to this one. So what do we see about this curve here? First of all, if it is a smooth curve, it is going to be a constant, the velocity is increasing uniformly at equal time intervals. So how do I know that the velocity is increasing here? Here we notice that the gradient is increasing. When the line tends to the vertical or tends to becoming vertical, it means that the gradient is increasing. The gradient is increasing for this line here. When the line tends to becoming vertical, the gradient is increasing. And if gradient is increasing, it means the velocity is increasing. And an increase in velocity is an acceleration. So this means the body is accelerating in this case. However, if this curve is a smooth curve, it means the velocity is increasing uniformly. If we have a smooth curve, it means the velocity is increasing uniformly. And smooth increase in velocity is called a uniform acceleration. So this is going to be a constant or uniform acceleration. Okay, so I think those are going to be the most common displacement time graphs you'll always experience in your exams. We have seen where the velocity is constant but not zero. We have seen where the body is, we have compared high speed, high velocity and low velocity but uniform. We have seen a situation where the body is at rest for a displacement time graph where the line was horizontal. We have seen a situation where the velocity was decreasing. We have seen a situation where the velocity was increasing. And we have seen a situation where the body is on a return journey or is going backwards, moving back to where it started from for a displacement time graph. So we have seen the gradient is the velocity. So let's see how we can now deduce a velocity from a displacement time graph. So let's consider a simple graph like this one here, and we should be able to deduce the velocity from this graph. So this is a graph of displacement S measured in meters against t in seconds. So can we determine the velocity from, can we deduce the displacement? Can we deduce the velocity from this graph? Of course we can. So you notice that the displacement increases steadily at first, up to around 3 seconds, but after it becomes constant, and we say the constant displacement means the body is now at rest. In other words, initially the car must be moving with a steady speed. This is going to be a steady velocity or steady speed because the gradient is the velocity. So this is going to be steady or uniform velocity. Then here, when we reach here, we notice that we have a horizontal line where here the velocity is going to be zero. The body is going to be at rest. So in other words, initially the car is moving at a steady velocity, but then it stops moving. The velocity after 3 seconds, is going to be the gradient of this line here. So we have to obtain this from the gradient. So when I draw a right angled triangle here, I need the rise and the run to find the gradient. So the gradient, the velocity is equal to the gradient of the displacement time graph. And from the graph, v is going to be equal to the change in the displacement over change in time. That is the same as the gradient. The change in displacement is delta s, and the time is going to be 3 minus 0. So when we substitute, we have 7, I think. Yeah, this is 7. This is 1. So 7 minus 1 over 3 minus 0. And this gives us the velocity as 2.0. So we shall always find the velocity from a displacement time graph as simply the gradient. Every time we have a velocity time graph, we should be able to find or establish the velocity by simply obtaining the gradient. Okay, I have a quick self-check for you that you can try out. The table shows the displacement of a racing car at different times as shown as it travels along a straight track during a speed trial. We have displacement and time. So they have given us values of t equal time intervals. Determine the car's velocity. Of course, I expect that when you sketch the graph or when you plot a graph, you should be able to determine the car's velocity. Draw a displacement time graph and use it to find the car's velocity. So, of course, here before the first question, you can find the velocity without, since there is no change in direction, you see that this is just increasing. So I can determine the average velocity as simply a displacement divided by t, which will be 340, divided by 4, which I think is 85 meters per second. Because there's no change in direction, I just get the displacement will be the same as total distance. So then you can draw a displacement time graph. You can pick a graph paper and then draw a displacement against time graph. Time is in seconds. So I think from 0 to 85, when I add 85, let me see, that's 170 plus 85. Yeah, this is a perfect straight line. If you plot this, you're going to get a perfect straight line. And then if you use it to find a gradient, the velocity will be equal to the gradient of that line. And I'm very sure you'll find, you may draw a right angle triangle, take readings of 2 points, and I'm sure you'll be able to get 85 meters per second. You can try that at your free time. A car travels due south. A car travels due south. The distance it travels at hourly intervals is shown in the table. So this is times plus 23 plus 23 plus 23. So this is going to be a straight line. Draw distance time graph to represent the car's journey. So this is just going to be a straight line to the origin. This is distance against time. So it is distance in kilometers against time in hours. So you can try to plot this on a graph paper or in a squared book, you will get a straight line. So you can do that. From the graph, reduce the car's speed. Speed will be called the gradient. Because there is no change in direction, I expect that your answer should be approximately 84 divided by 4. Approximately 21. So answer should be approximately 21 from the graph. What is the car's? They said from the graph, reduce the car's speed in kilometers per hour during the first 3 hours of the journey. First 3 hours of the journey. After 3 hours, the distance is 69 kilometers. So I can see 69 divided by 3. So you should get 23. Let me see, what is 69 plus 23? Yeah, here, this is not. So the straight line stops at around 69. So after that, this decreases. I think it has decreased after that. So the line bends afterwards. What is the car's average speed in kilometers during the whole journey? So of course, for the average speed is total distance over total time. So you can plot the graph on a graph paper just for practice. Just for practice. Then let's talk about deducing acceleration. Of course, we have seen that we can deduce velocity from a displacement time graph. Then how about acceleration? Of course, we can deduce acceleration from a velocity time graph. So we should talk about velocity time graphs. We should talk about velocity time graphs. So we are much aware from IGCSE that the gradient of a velocity time graph is actually the acceleration. You must have mentioned this in IGCSE. The gradient of a velocity time graph is the acceleration. The gradient of a velocity time graph is the acceleration. You mentioned that in IGCSE. So the gradient of a velocity time graph tells us whether the object's velocity has been changing or it has been changing at a high rate or at a low rate or not at all. So if it has been changing at a high rate, then we can say it has a high acceleration. If it has been changing at a low rate, it has a smaller acceleration. Or if it has not been changing, we say it has not been accelerating. So we can deduce the value of acceleration from the gradient of the graph because we know from IGCSE that acceleration is the gradient of the velocity time graph because by definition it is the rate of change of velocity. The rate of change of velocity, that's change in velocity over time taken, that is acceleration. So to begin with, let's consider a body moving or an object moving with a constant acceleration. Constant acceleration means the gradient of the graph should be constant. And remember, to have a constant gradient, the line must be straight. If it is constant and not zero, the line must be not horizontal. So for an object moving with a constant acceleration, a graph of velocity against time would look like that. It is a straight line, but not giving us a zero gradient. So a straight line with a positive gradient shows a constant acceleration because the acceleration is the gradient. So if I try to find the gradient of this line, it is going to be constant and positive. So a straight line with a positive gradient or a straight line with a positive slope shows constant acceleration. If we have two lines, the one with a greater slope or the one with a greater gradient should therefore be having the greater acceleration. For example, if I can illustrate this with the two graphs, compare graph A and graph B, you notice that I said a line which is closer to the x-axis is less steeper. A line which is closer to the y-axis or which tends towards the y-axis is more steeper. So it means line A is more steeper than line B. So we say A has a higher gradient than B. And remember, the gradient is the acceleration for a velocity time graph. So the acceleration of A is higher than the acceleration of B. The steeper the line, the higher the acceleration. That is, if we have an acceleration time graph. Okay. Let's also see a situation where the velocity is constant. For a body which is moving at a constant velocity, the velocity is not changing. This is a velocity time graph, remember. So if the velocity is not changing, we expect to have a horizontal line. So if the velocity is not changing, then you expect to have a horizontal line for the velocity time graph. And if you try to find the acceleration here, remember the gradient of the horizontal line is zero. The gradient is zero for a horizontal line. And remember, the gradient is the acceleration. So here the acceleration is zero. So whenever a body is moving at a constant velocity or steady velocity or uniform velocity, the acceleration is zero. So the velocity is constant, the slope is zero, therefore the acceleration is equal to zero. So now people will confuse this with the line we drew for displacement against time. Displacement S against time for constant velocity was a line like this. But here we are saying velocity against time for constant velocity is a horizontal line. So this line, this leads us to this. If I can deduce a graph of velocity against time from a graph of displacement against time, it should give me a horizontal line. So from the displacement time graph, we can obtain velocity. So this line here has a constant gradient. So if I'm to plot a graph of velocity against time by using the information from the graph of displacement against time, I should get a graph of that nature. Then suppose the body is on its return journey, or it's not necessarily return journey. Suppose the body is moving with a decreasing velocity. So decreasing velocity, now we normally confuse decreasing velocity with a body being on return journey. For decreasing velocity, the gradient of a displacement time graph is negative. I mean, for return journey, the gradient of a displacement time graph is negative. But for decreasing velocity, it means the acceleration is going to be negative. So the gradient of a graph of velocity against time is going to have a negative sign. So if the line tends towards the x-axis, it means the velocity is decreasing because this is a velocity time graph. And a decrease in velocity is a deceleration. If I try to find the gradient of this line here, this gradient is negative. It is a negative slope. So a negative slope will show a deceleration. Or we would say that the acceleration is negative. It is not the same as saying the velocity is negative. So here a negative acceleration does not mean necessarily that the body is moving in the opposite direction. No. A negative acceleration simply means the body is slowing down. Yet a negative velocity means the body is moving in the opposite direction. So we should note the difference between those two. A negative slope in this case is showing that the gradient is negative, and a negative gradient for velocity time graph indicates that the acceleration is negative. Negative acceleration is what we call a deceleration, not necessarily that the body is moving in the opposite direction. The body may be continuing in the same direction as before, but is slowing down because that's why the velocity is decreasing. So the equivalent to this for a displacement time graph would be a graph like this one here. This is a decreasing velocity, so the gradient should be decreasing. So I'll draw a smooth curve like this. Because this smooth curve of displacement against time means that the gradient is decreasing, and the gradient, remember, is the velocity. The gradient is the velocity. So if I find if the gradient is the velocity, it means the velocity is decreasing. So this curve also means a decrease in velocity. And a decrease in velocity is what we call a deceleration. But remember, the difference between these two is that this is a displacement time graph, and yet this is a velocity time graph. That is the difference between these two curves. Okay, suppose the body is moving, but this time with a non-uniform velocity, not with a uniform velocity. So if we think of a situation where the body is moving with maybe non-uniform acceleration or non-uniform deceleration, then it will no longer be a straight line because uniform should be referring to a straight line. So if we think of a situation where the body is moving but not with a uniform acceleration or uniform deceleration, so we have two important scenarios here. The acceleration is not uniform, which means either it is increasing or it is decreasing. This is a graph of velocity against time, and remember the gradient is the velocity. Whenever the line becomes horizontal, it means the gradient is decreasing. So the gradient of this line is decreasing. Gradient is decreasing. At this point here where the line is horizontal, the gradient is 0. And if the gradient was decreasing, it means the acceleration was decreasing because the acceleration is the gradient. It was decreasing to 0. So the body's acceleration was not constant, but it was decreasing to 0. So the slope is changing, meaning that the acceleration is changing. It is not constant. In this case, the acceleration is decreasing. The acceleration in this case is decreasing because the gradient is decreasing, but not decelerating. Now that is the difference. People think a decreasing acceleration is a deceleration. Not true. The acceleration is decreasing, but it is not decelerating because it's not negative. The acceleration changes from a high positive value towards zero, not going to the negative side. So the gradient is decreasing, the body is accelerating, but with a decreasing acceleration. It is moving, the increase in speed is becoming smaller. For example, the body starts with a speed of, the body starts increasing, starts let's say at 2 meters per second. Then it increases the speed by 4, maybe it increases the speed by 3, increases the speed by 2, increases the speed by 1, and finally it does not increase the speed anymore. So it means the acceleration is decreasing. The rate at which the speed increases becomes smaller, but it is not decelerating. Instead of increasing the speed with a bigger value, it is increasing with the speed with a smaller and a smaller value. So it is not decelerating, but the acceleration is decreasing. So we say that acceleration is decreasing because the gradient is decreasing, but not decelerating because the velocity is not decreasing. We only have deceleration when the velocity is decreasing. In this diagram, you don't see the velocity decreasing. You don't see the graph turning towards the x-axis. As an assignment, sketch a velocity time graph showing increasing acceleration. I think this one is easy. So a graph of velocity against time for increasing acceleration is just going to be the opposite to this one here. So because this was becoming horizontal for decreasing acceleration, the other one should be becoming vertical for increasing acceleration. So that is increasing acceleration. The gradient should be increasing. The gradient increases, which means the acceleration is increasing. I said when the line tends to becoming vertical, you should understand that it means the gradient is decreasing. So this is increasing gradient. Okay, so the graph should look somehow like that. I don't want it to look like this. Okay, so that is increasing acceleration. Okay. So let's see how we can deduce the acceleration from a velocity time graph. But before we look at this, we should be also able to sketch a velocity time graph for a stationary body, a stationary object. We should be able to sketch a velocity time graph for a stationary object. If the object is stationary, remember velocity should be 0. So if I want to sketch a velocity time graph for a stationary object at rest, velocity time graph for a stationary object or object at rest, velocity against time. Velocity against time for stationary object. If the object is stationary, velocity is 0, so in that case, the line should be along the horizontal axis. So for a stationary object, the line should be along the horizontal axis. First of all, here the acceleration will be 0 because the velocity is also 0. The line is horizontal and is along the x-axis. This is for a stationary object. So this is stationary. or an object which is at rest. It has no velocity, so it looks like that. It should be horizontal. So how do we deduce acceleration from then a graph? We have already said that the acceleration is the gradient of a velocity time graph. So we should be able to deduce the acceleration from a velocity time graph by simply calculating this. And we have done this in IGCSE. If I have a graph like this one here, and I want to establish or arrive at a displacement, I want to arrive at the acceleration. Having known that acceleration is the gradient, then I should be able to find the gradient for this graph. So if I have a graph like this, then I just need the gradient for, say, the first 5 seconds. I want to find the acceleration here. So the acceleration is going to be change in v over change in t, which is the gradient, which in this case is going to be 20 minus 0 divided by 5 minus 0, which would give us 4 meters per second squared as the acceleration. So the acceleration is simply going to be the gradient, which is the same as the change in the velocity, divided by the time taken, and when we substitute, we get 20 minus 0 over 5 minus 0, which gives us 4 meters per second squared. As an assignment, I may ask you to sketch a velocity time graph for a stationary object. I think I've already sketched this. Velocity time graph for a stationary object. Graph for v against t. If the object is stationary, we have said the line will be along the horizontal axis because stationary object has zero velocity and zero acceleration. Note that at this point here, the body is moving at a constant velocity. Here the velocity is constant because the line is horizontal. And if the velocity is constant, here the acceleration is equal to 0. That means it was decreasing. At this point here, you see that the gradient is decreasing, which means the acceleration is also decreasing. That means at this point where we have a horizontal line, the acceleration has already reached 0. A few things we need to note from what we have been discussing. A few things that we should note very carefully from what we have been discussing. You'll find most of these graphs from in multiple choice questions. You'll find many of them in multiple choice questions. So it's better you really try to understand these graphs. Many of them will be in multiple choice questions and they will be challenging. So how do you tell? How can one tell whether the object is moving in the positive or negative direction? How can one tell whether it is speeding up or slowing down? So we need to note this very carefully. One knows an object is moving in the positive direction if the line is in the positive region of the graph. That is always above the x-axis. By convention, we consider above the x-axis to be the positive direction. So if you want to know that the object is moving the positive direction, look at the line. If it is above the above the x-axis, whether it is sloping towards the x-axis or sloping away from the x-axis, we know it is in the opposite. It is in the positive direction of motion. And I can illustrate this very easily by using this diagram here. So whether the line is, if we have a velocity time graph, we can know that the object is moving the positive direction, whether the line is moving away from the x-axis or it is sloping towards the x-axis. However, I want you to note that here the gradient is positive, here the gradient is negative, here the velocity is increasing, here the velocity is decreasing, but in the same direction. There has been no change in direction. In both graphs, the velocity is in the same direction. Although in the first graph, the velocity is increasing, and the second graph, the velocity is decreasing. Just like you may be driving on a highway, you speed up and then slow down. You are still moving in the same direction, but you increase the speed and you again decrease the speed in the same direction. So as long as the line is above the above the x-axis, we always consider the body to be moving in the positive direction. And One knows that an object is moving in the negative direction if the line is in the negative region of the graph. So if the line is in the negative region of the graph, that is below the x-axis, we always talk about the object being to be moving in the negative direction or in the opposite direction if it is a velocity time graph. The line can be turning towards the x-axis or away from the x-axis, but all we can believe is that it is in the negative direction. For example, when you look at this one here, the gradient could be positive for this one and could be negative for this one, but both lines are below the x-axis. For the first one, the velocity is decreasing in the negative direction. For the second one, the velocity is increasing in the negative direction. As long as the line is moving away from the x-axis, it is an increase. As long as the line is moving towards the x-axis, it is a decrease. Okay. So in other words, how do you know that it is speeding up or speeding down? So how do you know that the object is speeding up, or how can you tell if the object is speeding up or slowing down from the velocity time graph? By the way, I want you to note that if a line crosses over the x-axis from the positive region to the negative region, or vice versa from the negative region to the positive region, then the object has changed direction. If the line does not cross, then it is still in the same direction. So how do we know that the object is speeding up or slowing down? So an object is speeding up if the line on a velocity time graph is getting further away from the x-axis, and we shall say it is slowing down if the line is approaching the x-axis. This is easy to illustrate. Consider this the first graph. So here the line is moving away from the x-axis, so we say it is speeding up. Even this one is moving up from the x-axis, so it is speeding up. But this one is speeding up in the positive direction. This is speeding up in the negative direction. Then on the other hand, if the line tends towards the x-axis, then it is slowing down. So this is slowing down in the positive direction, slowing down in the negative direction. So slowing down on a velocity time graph means the line going towards zero. Speeding up um, on a velocity time graph means the line moving away from the x-axis. So you need to note this very carefully. But I said if and only if we by any chance get a graph or we get a situation where the line crosses the x-axis, then it means the body has changed direction. If the line crosses the x-axis, then we say the body has just changed direction. For example, if we have a velocity time graph like this one here, velocity against time, and we have a graph where the line goes and crosses the x-axis. So we can say this was in the positive direction maybe, and this is in the negative direction. So here, between the section of the graph, we say the body was slowing down because the velocity was decreasing. And at this point, the velocity becomes zero where it crosses the x-axis. But after here, we say the body is speeding up because the line is moving away from the x-axis. It is speeding up, but in the negative direction. There has been a change in direction. So when the line turns towards the x-axis, the velocity is decreasing, but it can still be in the same direction. When the line moves away from the x-axis, the velocity is increasing. So here velocity is decreasing, but in the positive direction, and here the velocity is increasing because the line moves away from the x-axis. However, velocity is increasing in the negative direction. So you should be able to identify a situation where the, uh, the body is speeding up or slowing down, irrespective of whether it is in the positive or in the negative direction. Speeding up, all lines move away from the x-axis, whether in the positive or negative direction. Slowing down or decelerating, the lines tend towards the x-axis, whether in a positive or negative direction. Okay, so let's sum up this with a simple understanding, with a simple trial question for us to sum up all these concepts that we have been discussing. So describe the type of motion in each stage. You can pause the video and try to demonstrate your understanding of what we have just explored. So between O and A, it is a straight line. Remember, this is a velocity against time. A straight line means uniform or constant acceleration. So this is uniform acceleration. O to A is uniform acceleration because the gradient is constant and not zero. A to B, the gradient is constant and zero. And it is a horizontal line. So it means the velocity is constant between A and B, uniform velocity or constant velocity. B to C, so here I have said uniform acceleration, and here I've said constant or uniform velocity. Then B to C, we notice that it's still a straight line, so we can talk about uniform or constant. However, it is a straight line going downwards, the velocity is decreasing, that is a deceleration. So because the velocity is decreasing, that is a deceleration, so I will say constant or uniform deceleration. But you may even find that the gradient here is higher than the gradient of OA. That means this deceleration may be higher than the acceleration in OA. Then CD is a horizontal line, so this is still constant velocity. However, the velocity of CD is lower than the velocity of AB. Then D to E, you see that is a curve of a decreasing gradient because the curve is becoming horizontal. It is a curve which is becoming horizontal. As long as the curve becomes horizontal, it means a decrease in gradient. So the gradient is decreasing and the velocity was tending towards zero, so it is a decreasing deceleration. Decreasing deceleration. Then F to G, you see that the curve is becoming vertical. And if the curve is becoming vertical, the velocity is increasing, of course, that is an acceleration. And the curve is becoming vertical, so we can say increasing acceleration. Then G to H, we notice that it is a straight line, so it is going to be uniform, constant, but then the velocity was decreasing, so it is a constant deceleration or uniform deceleration. Okay, so you should be able to describe motion using graphs. Okay, so I think I gave a clue on all these areas just for those of you to summarize for you what we have been talking about here. OA is uniform acceleration, AB is uniform velocity, BC is uniform deceleration or constant deceleration, CD uniform velocity but lower than AB, DE is non-uniform deceleration, or we can say decreasing deceleration. Oh, there is one I skipped, which is E to F. Between E and F, here the velocity is zero, where the body is at rest. Then F to G, the gradient is increasing, so it's a non-uniform acceleration. It is an increasing acceleration. G to H is a non-uniform deceleration, as simple as that. So I am saying you should be able to describe a motion in that nature or in that way. Okay, let's do one more illustration. The figure below is a sketch graph showing how the displacement of a car traveling along a straight test track varies with the time. Describe the motion and deduce the graph of velocity against time. So when we look at this graph between O to A, we see as if the curve is having an increasing gradient up to A. And remember, the gradient of a velocity time graph, a displacement time graph, is the velocity. So it's like here, because the gradient is increasing, we can say the velocity was increasing between O and A. Then after A, we see now the curve is curving horizontal. Here we see that the gradient is decreasing, so we can say the velocity is decreasing. And at B, the curve is horizontal, so at B, exactly B, the gradient is 0. So here we can say V is equal to 0. So from this graph, I should be able to deduce a graph of velocity against time. Velocity against time, I should be able to deduce that graph. So here, from O to A, the velocity was increasing. Because it's a smooth curve, I will draw a straight line. Then from A to B, the velocity is decreasing, so it just starts decreasing, but for a short time, and it reaches 0, so it should go to 0 in a short time. The time here, from O to A, the time is bigger than from A to B, so it should take a shorter time to go back to 0. Okay, so the velocity time graph may look something like that. Let's first describe the motion for this graph. So I've said between B and O, between O and A, the distance traveled in equal time intervals are progressively increasing. The velocity, which is the gradient, is increasing, so the car is accelerating. So between O and A, I can say increasing velocity, or I can say the car is accelerating. And when you become an expert, you notice that because it is a smooth curve, it means the velocity is increasing by equal amounts in equal time intervals, so you could also say uniform acceleration. But we can simply say the car is accelerating because the velocity is increasing. Then between A and B, we see that between A and B, the distances for equal time intervals are decreasing. The car is slowing down. So we can say between A and B, the car is slowing down, or the velocity is decreasing, or we say the car is decelerating because the velocity is decreasing. Remember, the velocity is the gradient. The velocity is the gradient. And finally, at B, of course, we can see that the gradient is going to be 0. So at B, we can conclude that the velocity is 0 at B because the gradient is 0. So the car is or should be at rest. That is if we want to describe this motion clearly. So O to A, accelerating, A to B, decelerating. O to A, velocity is increasing, A to B, velocity is decreasing. O to A, speeding up, A to B, slowing down. And of course, at B, it is at rest. Let's deduce a velocity time graph. Therefore, since we have a displacement time graph, we have to deduce a velocity time graph. So I said for the first motion, for the first part, here we have increasing velocities. Because it's a smooth curve, we are going to have a straight line for velocity. Then for the remaining part of time, we have a smooth curve which is curving toward the horizontal, which means the gradient is decreasing. So I said we shall have a graph which goes to 0. So the velocity time graph for that will look like that. The velocity time graph would look like something like that. From this displacement time graph, for the first O to A, the velocity was increasing. That's why you see a straight line moving up from the origin. Then A to B, the velocity was decreasing. That's why you see the line going back to 0. To explain this, from the displacement time graph, we can reduce the variation of velocity with the time by drawing tangents to the curve at regular intervals of time and determine the gradient of each tangent. So we could, if we were to find a gradient at each of these points, we would expect, or if it is a smooth curve, we would expect that The tangents increase at equal time intervals until reach point A. And after point A, the tangents or the gradient of the tangents decrease. For those who don't know, the tangents are those lines which touch the points. Of course, at B, the tangent would be just a horizontal line whose gradient is 0. So the plot of V against T gives the graph which I've showed besides. It would give such a graph. You notice that this confirms our descriptive interception that we have already mentioned early on, that the velocity is increasing and then it is decreasing, accelerating and then decelerating. This is an acceleration and this is a deceleration. So the velocity increases from 0 to a maximum value at A, and then it decreases to 0 again from A to B. So that will be the velocity time graph. You are going to be able to draw these graphs in an exam. You should be able to sketch them and you should be able to interpret them in the multiple choice questions as much as possible. So let's talk about deducing displacement, maybe from a velocity time graph. Most of these concepts relate to what we did in GCSE, so they are almost the same things. So let's see, we'll talk about deducing displacement from a velocity time graph. Remember from GCSE, you noticed that the area under the velocity time graph gives the displacement of a moving object. So let us consider a displacement or a velocity time graph of this nature, which is a horizontal line at 20 meters per second. So we are saying the area under the graph is actually the displacement as we saw in GCSE. So for an object moving with a constant velocity like this one, the area is actually the area of a rectangular shape. So let's say for the first 15 seconds. So the area under the graph with the time axis, is going to be the displacement. Of course, because the velocity is constant, it's the same as saying velocity times time, but not all cases that the velocity will be constant. So for such an object, we notice that the displacement is going to be equal to the area under the graph. And in this case, the area is going to be in the vertical. We have 20 meters per second times the time axis, which is 15 seconds. And the unit seconds cancels out. So you have 20 meters times 15, which gives us 300 meters. So in case the velocity is constant, you could also use displacement as velocity times time if the velocity is constant. But if the velocity is not constant, then you can't say displacement is velocity times time. It is better you just consider the area under the graph. So for an object moving with a constant velocity, we could take this as the area of a rectangle, which could also be velocity times time. Suppose we have a changing velocity, such as in this case where the velocity was increasing. So here you cannot still say area times time as we said in the first case. So in the second case, for changing velocity, again we consider the area under the graph and it should give us the displacement. But for this case, or for this simple case, the area is a triangle rather than a rectangle because the speed or the velocity is not constant. So here the displacement, like I said, I always use the letter S for displacement instead of, it is not for speed. So here the displacement will be equal to the area under the graph. We know the area of a triangle is a half times the base times height. So this will be a half. What would be like the base is 5 seconds times what would be like the height is 10 meters per second. So per second cancels with the seconds. So you remain with a half times 5 times 10 meters, which gives you 25 meters. So that is how we determine the area, how we determine displacement from a velocity time graph. We take the area under the graph. Now here I considered the basic examples, but sometimes we may have very complex velocity time graphs. So I want you to note something very important. Of course, the ones I have just elaborated or the ones I've illustrated, you saw them in GCSE. But for AS level, you may not find simpler shapes like the ones like a rectangle or triangle. So in case the shape is not as simple as we have seen, for more complex graphs, you may have to use other techniques such as you may need to use a technique such as counting squares to deduce the area, but this is still going to be equal to the displacement. You may be forced to count the number of squares. You may be forced to count the squares, especially if the shape is not regular. Many times, if the examiner wants you to count the squares, the shape is such that the number of squares to be counted is smaller, or the shape is such that you can come up with other shapes. So in this case, you might, when using the method, you may need to note the scale. You may need to know the scale to know what the sides of the square represent, or what one small square would represent in area. And it is very important to note that the equations of motion, which we are going to discuss later on, will only apply to the object which is moving at a constant acceleration. So you can still not use equations of motion that we are yet going to discuss. So in a case you have a graph which is more complex, you still have to find the area under the graph. The first thing you need to note is the scale, to know what one small square would represent in area. And you should not be tempted to use the equations that we are going to discuss shortly. If the acceleration was changing, you wouldn't know what value to put in the equations. So constant acceleration will sometimes be referred to as uniform acceleration or steady acceleration. So constant acceleration will sometimes be called steady acceleration or uniform acceleration. So here you will not be tempted to use the equations of motion to find the displacement. We are going to see the equations of motion after this, perhaps in lesson 3. So you must find a way of finding the area under the graph, and I want to give you an example in that case. So let's consider an example which is a little bit more complex, where the area is not a regular shape we are used to, such as a rectangle or a square and so on and so forth. Let's consider a graph of this nature, and we want to find maybe the displacement in the first 20 seconds, maybe. The displacement in the first 20 seconds. Before we find the displacement, let's first talk about the acceleration. Of course, when you look at the graph, you notice that the gradient of the graph is decreasing. So it's like the acceleration is not constant. The acceleration at 10 seconds may not be the same as the acceleration at 20 seconds. So the acceleration at 20 seconds is different. So if I wanted to find the acceleration at 20 seconds, of course, I would draw a tangent at 20 and I find the gradient of that tangent. So in this case, I drew a tangent at 20 seconds, and then I find the gradient of the tangent by drawing the right angled triangle, where on the vertical I have, I think this is 10, 15, 16, 25, 26, so that is 26 minus 16, which is 10. On the vertical I have 30 minus 10, which is 20. So for the acceleration, for the acceleration is going to be the change in the velocity divided by the change in t. So the change in the vertical, this is change in the vertical divided by the change in t. So this will be equal to, for the acceleration to be 10 divided by 20 at 20 seconds. But it's not the same value at every point. Therefore, we can't use the method of equations of motion to find the displacement. I'm saying, or later on I will emphasize that we shall use the equations of motion only if the acceleration is uniform. So the velocity time graph here shows a non-uniform acceleration. In fact, it is a decreasing, it is showing decreasing acceleration. Determine the acceleration at the time of interest. Any time of interest, we said we mark a point on the graph that at the time you want to find. For example, here I wanted to find at 20 seconds. Then draw a tangent to the curve at that point. So I draw a tangent. A tangent is a line which touches just that point evenly and uniformly. So you try to balance this line so that it does not enter into the curve. So that is a tangent. Then of course you now draw a right angled triangle and use it to use the right angled triangle to find the gradient. So make a large right angled triangle and use it to find the gradient. That's what exactly I've just done here. And in this case, the gradient is going to be 0.5 meters per second squared, which will be the acceleration. So in case we want acceleration at any time or at any point, remember to draw a tangent at that point. I think that one is easy. In case you want to find the acceleration at any point, remember to draw a tangent at that point. Then the next thing is, suppose I want to find the displacement from a velocity time graph. That's what I'm interested in. To find the acceleration is easy, you just do a tangent at that point. To find the displacement, say for the first 20 seconds, I want you to note that for the first 20 seconds, this is not a regular shape. So how do I find the displacement? So to find the displacement, let's say for the first 20 seconds, then we must find the displacement of the body as it accelerates. We can determine the area under the velocity time graph using several methods. But here we want to find, let's say, the displacement for the first 20 seconds. So I said we must find a way of finding the area under this graph because we don't have a regular shape. So for the first 20 seconds, let me change the color to this, maybe green. So first 20 seconds stops here. There are several ways of finding the area of this, but the easiest would be counting the squares. However, the squares may be many. So to find the displacement of the body as it accelerates, we can determine the area under the velocity time graph. And for the first 20 seconds, there are about 250 small squares, and each square represents 1 meter per second on the y-axis and 1 second on the x-axis. So you must find a scale. Here we have from 0 to 10, we have 10 small squares. So here it means one small square on the x is 1 second. One small square on the y, we have 0 to 5. One small square on the y is also 1 meter per second. So it means the area of one small square is 1 times 1, which is 1 meter per second times 1 meter, which is just 1 meter. So one small square in area, one square represents 1 meter. That is one square. So one square represents 1 meter in area. Since I have 250 small squares, so that is going to be approximately 250 meters. Of course, this method is going to be tedious. Imagine counting all these squares from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And remember, not all the squares may be full. Some of them are going to be half. So you have to combine the half squares. So this method would be tedious. So this method could be tedious, but you can save yourself a lot of time by drawing a line from the origin to 20 seconds. So instead of counting all the 250 small squares, I would draw a line I would draw a line from the origin up to 20. So when I draw that line, I now have a triangle whose area I have a triangle. The area of the triangle, here the area is going to be equal to a half times the base, which is 20, times the height, which will be, I think this is 21 times 21. So I get the area of the triangle, which is going to be approximately, let me see, I think this is 210 meters. That is the area of the triangle. So it means I now remain with very few areas, very few small squares to count. So the area of the triangle is easy to find. And then you only count the number of squares between the line you have drawn and the curve. So it now becomes easier for me to count. Let me try to count the full squares first. I'm looking for full squares first. So let's say this is 1, 2, approximately 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So approximately 22 full squares. So it means, remember, each full square is 1 meter. So I'll say plus 22 meters, then plus half squares. I have to count the squares which are not full. So I will just change the color. For half squares, I have 1 at the bottom, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me count on top first. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, about 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, around 50. So about 50 half, 50 half squares. So for half squares, because one full square has an area of 1 meter, for half squares to be half of 1 meter. So for 22 full squares, the area is 22 meters. For 50 half squares, the area is going to be 50 divided by 2 meters, which is going to be 25. So I'll add plus 25 meters. So the total area is going to be 210 plus 22 plus 25. 210 plus 22 plus 25. 210 plus 22 plus 25. So this will give me 257 meters. So this will be an estimated value of the total area under that graph. So the examiner, of course, will give a limit, maybe between 250 to 260 and so on and so forth. So that is how we find the area under that graph. You can see what shape you can draw inside, whose area you can easily calculate. Then know the scale, what one small square represents in area. After calculating the area of the shape you can easily calculate, then count the full squares and add their area there. Count the half squares. For half squares or squares which are not full, the area of one full square is divided by 2. That's why I said 50 over 2. So I added 25 here. Then sum up to find the total area. So that is that is the only method you can use to find the area if you don't have a regular shape that you are used to find the area. So the area under the graph is going to be equal to, or the area under the graph is going to be the displacement. The area under the velocity time graph is going to be the displacement. Okay, here is a self-check. The velocity time graph represents the motion of a car along a straight road for a period of 30 seconds. Describe the motion of the car. So it is a straight line. That means the acceleration is constant but the velocity is decreasing. So it is a uniform deceleration or a constant deceleration. From the graph, determine the car's initial and final velocity over 30 seconds. Initial is 20, final is, I think final is 8. Acceleration, we find the gradient. Acceleration is going to be final or 20, no, acceleration is going to be 8 minus 20 divided by 30 minus 0. The acceleration is negative. By calculating the area under the graph, determine the displacement. So you find the area under this graph. So this is a trapezium. Or you can divide it into two shapes, a rectangle and a triangle. And then you find the area with the x-axis. So you find the area with the x-axis. Some people will only cut off the triangle and find the area of the triangle. You find the area with the time axis. So that is a trapezium. So you can use any method. So by calculating the area under the graph, determine the displacement. So you can use this as a triangle, which is a half times 30 times 20 minus 8, which is 12. And this one is 30 times 8. So this is, I think this is 6. This is 180 plus 240, 240 plus 180. I think this is going to give us a total of 420 meters. Or you can use the formula for a trapezium to find this. So for a trapezium, the distance is going to be equal to a half. One side should be A, maybe let's say A is 20 plus B, which should be 8. This would be A, the other one would be B. Then the height will be maybe times 30. This is going to be the H. I'm using the area of a trapezium, which is a half into A plus B times H. So this is going to be 24 times 30 divided by 2. Is it? No, 28. 28 times 30 divided by 2, which is 240. I mean 420. Check your answer to part D by calculating the car's displacement using U. S is equal to UT plus half AT squared. So S is displacement, U is initial velocity, which is 20 times T, which is 30, plus a half. Acceleration is negative. What is the acceleration? The acceleration is going to be negative. What is this? 8 minus 2, that is minus 12, divided by 30, negative 0.4 meters per second squared. So times negative 0.4, then times t, which is 30 squared. I think this should give you 420 meters. You can verify that. I must have given the answers to these questions. The car is slowing down with uniform deceleration, that is constant deceleration. So initial and final velocity, the acceleration, I think those answers are correct. The graph below represents the motion of an object moving with a varying acceleration. Lay your ruler on the graph so that it is tangent to the graph at point P. What are the values of time and velocity at this point? So you can put there your ruler and see the value of t. I think 7.5 is fine. Of course, you should have a scale. One box on the x-axis is representing 5 divided by 10, that is 0.5 seconds. So I think P should be 7.5. estimate what are the values of time and velocity. So velocity, you just read here. I think 220 is correct. One box on the vertical represents 100 by 10, which is 10 meters per second. One box, that is one square. Here, one square was 0.5. Estimate the object's acceleration at this point. So I said for velocity time graph, to find the acceleration at a given point, you draw a tangent at that point. You draw a tangent at that point, and the tangent should be symmetrical. In other words, should be well balanced, not entering into so you can draw a better tangent than mine, and then you draw a right angled triangle. So you find the acceleration from the change in v on the vertical over the change in t. So you should be able to get approximately 20 meters per second. You can try that at your free time. A car is traveling at the speed limit on a motorway. Ahead the driver sees hazard lights and gradually slows down. He sees that an accident has occurred and brakes suddenly to a halt. Sketch a velocity time graph to represent the motion. So it was moving at a speed limit. That means it was moving at a constant speed. Ahead, the driver sees hazards and gradually slows down, so the speed decreases. He sees the accident and brakes suddenly, so it means again the speed decreases, but this time it decreases very rapidly. So sketch a velocity time graph. So if I was to sketch this to give you just a sketch of this velocity time graph, initially the speed is constant, then it slows down, then it rapidly stops. So this is going to be very sharp. So it is something like this. Is traveling at a speed limit, that is at a constant speed, then slows down, speed decreases, and then rapidly stops. It's almost vertical because it rapidly stops. So the graph should somehow look like this. You can draw a better graph. And lastly, the table below shows how the velocity of a motorist changes during a speed trial along a straight road. Velocity, time, draw the velocity time graph. So you should be able to draw a velocity time graph. You notice that the velocity first increases from 0 to 15 to 30. It remains constant at 30. It starts decreasing. But there's been no change in direction. So it means it's decreasing but in the same direction. Then from the table deduce the motorist's acceleration during the first 10 seconds. So for the first 10 seconds, I see equal increase in velocity, so I can just say 30 divided by 10, which is going to be from the table deduce the motorcyclist's acceleration during the first 10 seconds. So during the first 10 seconds, I think it's just going to be 30 divided by 10, which is 3. So this is 3. Check your answer by finding the gradient. Of course, this should also be 3. If you sketch, you look at your graph. Then determine the motorcyclist's acceleration during the last 15 seconds. So the last 15 seconds, you should use the graph. So the last 15 seconds from 20 to 30, we notice that the velocity was decreasing by equal amount. So it is going to be 0 minus 20 divide by the 10, which the 15 seconds. So I think the answer is going to be minus 2 meters per second. You can check from the graph you have plotted. Then determine the motorcyclist's acceleration during 15 seconds. So that one we have seen, the last 15 seconds. Use the graph to find the total distance traveled during the speed trial. So the total distance is going to be the total area. Total area under the graph. So you can sketch your graph or plot your graph. These numbers are easy to plot. You don't even need a graph book. You need just a squared book. Then plot your graph and try to use those values to find the acceleration and then the distance traveled as the area under the graph. I think in lesson 2 we have entirely described the motion using graphs. In lesson 1 we described the motion using words. In lesson 2 we have described the motion using graphs, the speed time graph, velocity time graph, displacement time graph, and so on and so forth. So in lesson 3, I think we shall now describe motion using equations or uniformly accelerated motion. So let lesson 2 stop here. Until next time, bye bye.